So, as I mentioned last time, we're going to start an example problem here. I've pulled this out of some old notes. It's indicating this is number 352 from the Hibbler text. I've also written myself a note that a recent Fundamental 311 is very close to this with slightly different numbers. I'm going to work this one. This is probably not 352 in your text, but you might be able to find one like it. And if not, that's okay. I don't mind working examples that aren't just like the ones you have in your book. But so you can kind of see what it's going to look like. A cable here, a cable here, a cable there, and then a weight hanging off right here at point A. And that's out here at a point along the x-axis. So I'm going to draw this with you so you can draw it in your notes. This particular problem they've drawn, now they've continued to keep z in the vertical, which is normally, for me, that's a good idea. You don't necessarily have to draw z in the vertical. It's kind of up to you what direction orientation you want to draw things, but that's a very common thing to do. This one does draw x kind of off to the side out here. X goes out here quite a ways. Move up just a bit so we can see that being x. And then the y-axis, instead of being straight out left or where right is positive y, this one draws y down just a little bit, which is okay. We talked about right-hand rule. So long as I go from x to y when I close my right hand, the fingers on my right hand, my thumb needs to point in the z direction. So from x to y, my thumb is pointing up in the z. That is a fine orientation. So you can draw this any way you like, so long as you follow that right-hand rule, you're technically correct. Okay, there's a point C back here on the ZY plane. Point C. The problem says that it is 8 feet straight up in the Z direction. So if you dot a line parallel to y over there, this is going to end up here at 8 feet tall. And then C is going to be, the problem will basically put you kind of a distance here and say that this distance is 9 feet. And my preference is to mark that on the y-axis and say, well, that's a positive 9 feet out here on the y-axis. And then there's a point B back here on this wall of the ZY plane. It's in the negative y direction, positive z direction. It's not quite as high up. So back here you've got point D. And point D is 6 feet up on the positive z-axis. And it is 4 feet on the minus y-axis, so minus 4 feet. And the way they would mark this is they would say, well, you've got 4 feet here, and they would say you've got 6 feet there, something like that. This should be more vertical than I've drawn it. Okay. So that's points C and D. Out here along the x-axis, there's a point A right on the x-axis. Out here a distance of 12 feet. There's point A, that is a knot, basically, or a ring. And then a little further out on the x-axis, out here at 18 feet, you have another point, and it's kind of attached to a wall out here. Point B. Now what you have is you have a cable going from A to B. You have a cable going from A up to D and A up to C. So I'm going to dot this in, just kind of in the general direction, because if I draw it solid initially, it's going to be, I will get that wrong and it won't look right. But if I've got just a few dots that I can kind of easily connect, it's a lot easier to make a cable. Doesn't have to be great, just has to kind of look the part. And then also a cable from D to A. So I'll do the same thing. I'll kind of dot in a line from D Once I've kind of got an idea of where that's going to go, I'll solidify that. So I've got a line from A to D. And then at point A, we are suspending a weight. A 60-pound weight. Okay. Not too bad. Not the best drawing I've made of this before, but not too bad. The problem will say, find the tension in each cable. Okay. Now, as we said in the previous discussion, the previous video, we said we're going to use position vectors to describe the tension in cables. What am I looking for? I'm looking for the magnitude in each one of these cables. I'm doing the magnitude in TAB, the magnitude of TAD, and the magnitude of TAC, and we'll follow some procedure like this. I can write a position vector from A to each of these points, and then I can write generate a unit vector from that position vector and use that unit vector then to describe those tension vectors. So, what does that look like? Come on. A couple blank sheets of paper here. Okay. So this is continuing lecture 5. This is page 2 of something. Okay. So if I want to write these points then in x, y, z coordinates, point A is going to equal, point A is out here on the x-axis, so that's a positive 12, 0, 0. And point B is 18, because it's a little further out on the x-axis, so it's 18, 0, 0. Point C up here, point C has an x value of 0. It's on the zy plane. It doesn't come out into this x value. It's right here at 0. It's in the it's parallel to the origin there, so to speak. Now, on the y-axis, it is 9 feet from the origin out on the y-axis. So that is a positive 9. And then it is up 8 feet on the z-axis. So it is 8 feet above the origin on the z-axis. Point D is also on the zy plane, so it has a 0x value. Point D is out on the y-axis. It is 4 feet from the origin out in the y direction, but it's minus 4. It's 4 feet back here to the left, so it's minus 4 in the y direction. And then it is up 6 feet from the origin to get to D, 6 feet above, so it's a positive 6 on the origin. And each of these are feet. You need to be good engineers here and keep track of our units. Problems are always incorrect if they don't have units. Now, could you get by not writing units as you go? Yes, and in statics you could really get by not writing units as you go. When you get to a class like thermo or fluid mechanics, thermodynamics or fluid mechanics, or even heat transfer, you will spend so much time trying to find unit errors if you're not in the habit of writing your units in your calculations. My philosophy is this: I don't force you to write units in your calculations. The amount of time you will waste trying to find unit errors at some point in your life will force you to learn the hard way to write units as you go. So I find I don't have to teach you that. I mean, I try to tell you to, but anyway, I digress. Let's write position vectors. Position vector from A to B. Let's write position vectors because, again, what am I trying to do? I'm trying to find the tension in each of these cables. How do I do that? Well, I'm going to use equilibrium. I'm going to write sum of forces in the x, y, and z, but I need to be able to describe these cables in the x, y, and z directions. How am I going to do that? I need position vectors. So let's write position vectors for each of these cables. I've got a cable going from A to B, right? So its position vector is going to be b minus a, final minus initial. It's going from a to b. So it's going to be in the x direction 18 minus 12. 18 minus 12, that's in the x direction. In the y direction, notice both of these have 0 coordinates in the y. So it's 0j plus 0k. It's 0 minus 0 in the other two directions. So, and these are all feet. So position vector from A to B is just going to be 6i feet. That's it. Okay. Position vector AC going from A to C. So C is the final. We're going to take final minus initial. So C being the final, that's 0 minus 12 in the I. I'm going to put brackets on the outside, so I only have to write feet one time. C in the y direction is 9 minus 0. That's in the j. C in the z direction is 8 minus 0. That's in the k. And these are all feet. So RAC is going to be minus 12i plus 9j plus 8k, and those are all feet. Okay, that's two position vectors. I also have a cable running from A to D, so I need a position vector going from A to D to describe that cable. So R position vector from A to D. Alright, so D is this. My final is D, so I'm going from A to D. So it's 0 minus 12. That's in the I direction. Again, brackets on the outside, so I don't have to write feet one time. Plus, this is minus 4 is the final Y value. We're starting at 0, so it's minus 4 minus 0 in the J direction. Plus a positive 6 minus 0 in the K direction. And those are all feet. So position vector from A to D becomes minus, parentheses, minus 12i minus 4j plus 6k. Those are all feet. Okay, now what am I trying to do? Well, as I said earlier, if we refer back to my notes, I'm trying to write equilibrium equations, which means I need to know the x, y, and z components of all of these tensions. To find the tensions, I need to know the unit vectors. I need to know the unit vectors that describe each of these cables. The unit vectors can be found by taking the position vector, which we just found, divided by their magnitudes. So I need to know their magnitudes. Okay, so magnitude of AB, that's pretty easy. Just simply RAB. Oh, sorry. That's pretty easy. AB is 6 in the I direction, so RAB is just simply 6 foot. There we go. RAC, this one we're actually going to have to do math. So this is AC, so this is going to be square root of minus 12 squared. It's 12 feet squared, but minus 12 squared plus 9 squared plus 8 squared. And the units are going to end up being feet. Right? Go ahead and do your calculator. I think I've got this written down. Go ahead and do your calculator so you know how to find that. Okay, you got a value? I have written down here that that is 17 feet is the length of AC. And I'll let you go ahead and find RAD. I'm going to pause and let you find RAD. All right, how'd you do? Did you get 14 feet? That's what I got. You can see my calculations there. And that matches what I've written down in previous sets of notes. Okay, so what does that mean? again, what the heck are we trying to do? We are trying to find the tension in these cables. To describe the tension, I need a position vector. Well, actually, I need a unit vector. To describe a unit vector, I need a position vector divided by its magnitude. I now have position vector for all 3 cables. I now have magnitude for all 3 cables. Now I can find unit vectors for all 3 cables. So unit vector AB is just going to be, this is going to be, notice I've got 6I feet divided by 6 feet. Unit vector UAB, you actually could have seen this from the very beginning. It's just in the x direction, right? Notice this cable just points in the x direction, positive x direction. From here to here is going to point in the positive x direction. So just the I vector would actually have been sufficient for that one all along, but that's okay. It's okay to be able to prove that kind of stuff to yourself mathematically. Let's write the others. Unit vector from AC. So I'm going to take vector AC, right? 12, so minus 12 plus 9 plus 8. And they're all going to get divided by 17. So it's going to be minus 12 over 17 I. It's going to be plus 9 over 17 J. And plus 8 over 17 K. And each one of these is feet over feet. So a unit vector ends up being unitless. It's just a magnitude of 1, but some direction. So this describes basically the direction of that cable going from A to C, and we'll find the unknown tension in that to support the load that's there. Same thing with AD. Go ahead and write it out here. Pause if you would like. And so we'll pick up here. AD is minus 12 over 14 in the I. That's going to be minus 4 over 14. Feel free to reduce these fractions if you like. Not going to hurt my feelings. I'm probably not going to, but you can. Plus 6 over 14 K. In fact, all 3 of those could be reduced. You could at least pull a 2 out of all of them. All right, so now I've got a unit vector for all 3 of these. We're going to stop there and pick up on the next video and finish this problem.